The bat leaves its roost the way it has every night of its adult life, without hesitation, without light, without sight in the human sense. It drops from the cathedral darkness beneath the canopy and accelerates into open air, wings slicing humid night with mechanical precision. In a healthy forest, this moment is never a gamble. The bat's world normally blooms instantly around it, not as images but as structure, a three-dimensional map built from returning echoes, every wingbeat synchronized to a pulse of sound too high for human ears to register. Leaves become surfaces, gaps become corridors, insects flare briefly into existence as dense moving points. Tonight, that map never fully forms. The bat lunges anyway, jaws opening at the exact instant that should intercept prey, then closes on nothing. Air, silence. Momentum carries it forward into a clumsy recovery, wings flaring wider than necessary as it burns energy correcting a mistake it almost never makes. Echolocation is often described lazily as sonar, but that comparison undersells its brutality and elegance. For most Amazonian bats, sound is not a supplement to vision. It is vision. Each pulse is an active probe, a demand for information sent into darkness and answered by the environment itself. Echoes return with delays measured in microseconds, warped by texture, density, motion, and distance. A moth's wings do not just reflect sound, they smear it, fluttering interference patterns that trained bat brains read instantly as edible, evasive, or dangerous. This is not passive perception. It is continuous computation under extreme time pressure, performed while flying at speed through clutter dense enough to tear wings. When that acoustic feedback collapses, when echoes fail to return cleanly or at all, the bat is not blinded in a metaphorical sense. It is robbed of the only sensory currency its hunting strategy accepts. The immediate consequence is inefficiency, and inefficiency is lethal in small, high-metabolism animals. Bats run hot. Flight is expensive, and insectivorous species survive on margins measured in minutes and grams. One missed catch is not a disappointment, it is a debt. Tonight the bat circles longer than usual, wing muscles tightening as glycogen drains faster than planned. Each extra pass through the air compounds the problem. More flight means more heat, more water loss, more oxygen demand. Thermoregulation becomes harder as muscles work without payoff, forcing subtle shifts in wingbeat cadence and glide ratio that further degrade hunting precision. In a functioning system, echolocation keeps effort and reward tightly coupled. Remove the feedback loop, and the entire energy economy destabilizes. Below, the forest responds immediately, though not in ways most observers notice. Mosquitoes and other night-flying insects are not merely pests, they are mobile packets of energy and information moving between plants, animals, and water. Bats normally skim this flux with ruthless efficiency, removing vast numbers of insects before they ever interact with larger animals. As bat predation falters, insect pressure spikes, not explosively, but persistently. More insects survive each hour, and survival compounds. They probe more skin, land more often, linger longer on warm bodies. Birds at roost twitch and shuffle as bites increase. Mammals shift positions, waste energy swatting or moving, and expose themselves longer in open areas. Disease risk rises not because of any single pathogen, but because contact rates increase across the entire web. The forest grows itchier, noisier, more restless, even though the night itself seems unnaturally quiet. This is where silence reveals its real cost. Bats are not opportunists that can simply switch senses and adapt overnight. Their skulls, inner ears, vocal cords, and neural circuits are all sculpted around precision timing. Some species emit dozens of calls per second, dynamically adjusting frequency and intensity based on clutter and prey behavior. Their brains are wired to expect echo delays within narrow windows. Outside those windows, information is treated as noise. When the acoustic environment degrades, through sustained silence, interference, or echo distortion, the bat cannot just try harder. It flies more, calls more, spends more, and earns less. The predator is not injured, poisoned, or chased away. It is economically ruined. There is a cruel irony here. Silence feels safe to human intuition. We associate quiet with peace, with absence of threat. In the Amazon night, silence is a warning sign. The forest is normally thick with layered sound. Insects, frogs, distant birds, and above it all, the ultrasonic lattice of bats stitching space together. Remove one layer, and the others shift in response. Insects that normally evolved under heavy bat predation relax their evasive behaviors. Some moths reduce erratic flight patterns that would otherwise confuse echolocation, saving energy now that the threat feels lower. This makes them easier prey for birds at dawn, but harder targets for bats still struggling in the dark. The system does not rebalance cleanly, it wobbles. As the night deepens, the bat makes decisions it would never make under normal conditions. It pushes farther from the roost, gambling on unfamiliar corridors where echoes might behave differently. It hunts closer to water, where open space reduces acoustic clutter, but increases exposure to predators that hunt by sight or vibration. These choices are not strategic innovations. They are acts of desperation forced by sensory bankruptcy. Every minute spent flying without capture tightens the margin between survival and collapse. For pregnant or lactating females, the stakes are even higher. Milk production demands calories on top of flight costs, and missed meals echo forward into weaker offspring, delayed growth, and higher juvenile mortality weeks later. What makes this collapse so insidious is its invisibility. There is no dramatic die-off, no sudden silence of wings. Bats simply fail a little more often, arrive home a little lighter, reproduce a little less successfully. Over time, population curves bend downward, and the forest adjusts in ways that appear unrelated unless you understand the sensory foundation that cracked first. More insects mean more pressure on leaves and flowers, altering plant energy budgets and flowering times. Pollination schedules shift subtly, affecting fruit availability for animals that never interact with bats directly. A failure in sound perception ripples outward into changes in light, foliage, and seasonal rhythms. Silence in this context is not the absence of noise, but the removal of information. Bats evolved in a world where darkness was never empty. It was dense with data encoded in returning echoes. Their entire evolutionary gamble was that timing and precision could substitute for vision, allowing them to dominate a niche others could not. When that informational scaffolding disappears, even temporarily, it exposes how specialized and how fragile that dominance really is. The predator does not fall because it is weak, but because its entire survival strategy assumes a conversation with the environment that suddenly goes unanswered. By the time the bat finally returns to its roost, wings aching and reserves low, the damage is already done for this night. One missed insect means another survives to bite, to feed, to reproduce. One failed hunt stretches into dozens of altered interactions below. The forest does not need catastrophe to unravel. It only needs timing to slip. Silence does not just starve prey of warning. It bankrupts predators that live on precision, turning masters of the dark into debtors in an ecosystem that never waits for anyone to catch up. Mosquitoes are often framed as simple winners in a quiet forest, beneficiaries of any breakdown in the systems that normally keep them in check. That framing is lazy. In reality, a sensory blackout creates a paradox for them, one that plays out at wing-length distances and across entire floodplains at the same time. They gain territory while losing precision, abundance while sacrificing control. In the Amazon night, mosquitoes do not suddenly become better hunters when sound collapses. They become clumsier, they overshoot, misjudge, and waste effort. And yet, because the ecosystem around them is tightly coupled, those individual failures are drowned out by population-level success. A mosquito's world is built from gradients: heat, carbon dioxide, humidity, skin odor, and at close range, sound. All converge into a navigational funnel that guides it toward blood. This is not a straight flight. It is a zigzagging, constantly corrected approach, with the final seconds depending on cues so subtle they barely register as stimuli at all. The faint whine of wings from other mosquitoes can signal crowding or opportunity. The low-frequency vibrations from a host's movement help confirm proximity. Even the turbulent air around a breathing animal carries acoustic information. In a functioning night, sound does not replace chemical cues, but it sharpens them, turning a diffuse plume into a precise landing target. When that acoustic layer collapses, the mosquito's final approach degrades. It still smells the host. It still senses warmth, but its confidence erodes in the last meter. Flights become less efficient, more looping, more hesitant. Landings miss skin and strike hair, leaves, fabric, or nothing at all. Feeding attempts fail more often, interrupted by defensive movements that the mosquito did not anticipate in time. From the insect's perspective, this is a loss. Each failed landing is a risk. Energy spent without gain, exposure to being crushed or brushed away, precious time wasted during a narrow feeding window. Yet above this messy microscale struggle, something else is happening. The night sky holds more mosquitoes than it should. Their predators, the bats that normally vacuum the air, the night birds that pick them off at dawn, the frogs that thin their numbers along water edges, are missing or impaired. The same sensory disruption that makes a mosquito's targeting sloppy also bankrupts the animals that keep mosquito populations in check. Survival rates tick upward, not dramatically, but consistently. Eggs laid days earlier now mature into adults that would normally have been eaten. Larvae that would have been culled in mid-air reach breeding age. The population curve bends, and once it bends, it carries momentum. This is the core contradiction. Individually, mosquitoes perform worse. Collectively, they thrive. The Amazon amplifies small advantages relentlessly, and reduced predation is one of the most powerful advantages an insect can receive. Mosquitoes do not need to be good hunters if there are simply more of them. A sloppy approach multiplied by millions still produces more bites, more interruptions, more stress across the forest than a smaller, more efficient population ever could. Animals feel this shift almost immediately, though not always consciously. Mammals grazing or resting at night flick ears more often, stomp or swish tails, and change posture repeatedly. These movements cost energy and fragment rest. Birds at roost adjust positions, exposing themselves to cooler air or predators as they attempt to avoid concentrated biting. Even reptiles, with their slower metabolisms, shift basking and resting patterns to escape persistent harassment. None of this looks dramatic on its own. There is no panic, no stampede, but across hours and nights, the cumulative cost is real. Less feeding, poorer thermoregulation, interrupted sleep cycles. All of it erodes fitness in small, compounding increments. Mosquitoes, meanwhile, adapt behaviorally to their own sensory handicap. In the absence of reliable acoustic confirmation, they linger longer in odor plumes, probing cautiously rather than committing to rapid landings. This increases encounter time with hosts, which paradoxically raises the chance of a successful bite, even if any single attempt is less precise. The forest becomes saturated with low-level harassment. Hosts swat more often, but swatting is imprecise too. It disrupts feeding, but rarely eliminates the threat entirely. The interaction stretches out, favoring the sheer persistence of numbers over individual skill. There is an evolutionary irony embedded here. Mosquito sensory systems evolved in a world dense with sound and movement, where hosts and predators broadcast constant information. Remove one channel, and the insect's toolkit is suddenly mismatched to reality. But evolution does not optimize for perfection. It optimizes for survival under average conditions. When conditions change abruptly, the winners are not always the most specialized, but the most numerous. Mosquitoes occupy that category with ruthless efficiency. They are not dominant because they are elegant, but because they are redundant. As nights pass under these altered conditions, the forest's rhythms shift. Animals adjust feeding times, clustering activity into shorter, more intense bursts to minimize exposure. This creates brief windows of chaos, sudden surges of movement and sound that ripple outward through the food web. Insects other than mosquitoes benefit too, exploiting the same gaps in predation pressure. Leaf damage increases, sap flows change. Plants respond by reallocating resources, subtly altering growth patterns that will shape habitat structure months later. The mosquito surge is not an isolated phenomenon. It is one symptom of a broader rebalancing driven by the loss of sensory control at the top. From a human perspective, the result feels perverse. Remove sound, and biting pressure increases. Intuition says fewer cues should mean fewer successful parasites. Ecology says otherwise. Systems are coupled, and removing a constraint on one node can outweigh impairments elsewhere. Mosquitoes lose accuracy but gain immunity from being eaten. The trade-off favors them decisively. What makes this especially destabilizing is that the mosquito's impact is indirect as much as direct. The bites themselves are not the whole story. It is the behavioral tax they impose on every other animal that magnifies their influence. Time spent swatting is time not spent feeding. Time spent moving to escape bites is time not spent resting or thermoregulating. Stress hormones rise. Immune systems divert resources. Reproductive timing slips. None of this requires disease to matter. The ecological footprint of mosquitoes extends far beyond what they inject into skin. In this altered night, mosquitoes are both impaired and empowered, losers in skill, but winners in scale. They demonstrate a brutal truth about ecosystems. Success is not always about doing something well, but about existing in large enough numbers that failure barely matters. When predators lose their sensory edge, precision becomes irrelevant. Persistence takes over. By the end of the night, the forest does not feel louder or more alive. It feels irritated, unsettled, fractionally out of balance. The air hums with insects that cannot quite find their mark yet refuse to disappear. Mosquitoes have not conquered the Amazon through excellence. They have inherited it through coupling, through the cascading consequences of silence elsewhere. Removing one sensory channel did not weaken them enough to matter. It weakened everything that normally keeps them small. The forest floor looks unchanged at first glance. Leaves glisten with moisture, bromeliads cradle pockets of water, and the understory hums with latent life. But something essential is missing. In a functioning Amazon night, poison dart frogs stitch the darkness together with sound. Their calls are not background noise. They are spatial coordinates, biological timestamps, and social contracts broadcast into humid air. Each note carries information about identity, size, stamina, and location. Tonight, that acoustic scaffolding is gone. The forest is visually identical and behaviorally broken. Poison dart frogs are small enough to disappear beneath a human boot, yet their survival depends on occupying precise slices of space. Males do not wander randomly. They anchor themselves to calling sites, leaf litter near water, low vegetation, the edges of temporary pools, and advertise those positions relentlessly. Sound keeps order. It tells rival males where not to go, and tells females where to find a suitable mate without crossing hostile ground. In silence, that map dissolves. Frogs still move, still feed, still attempt to reproduce, but they do so without knowing where others are supposed to be. Territories blur, boundaries collapse. The forest floor becomes crowded not with bodies but with uncertainty. The first cracks appear in spacing. Normally calling males arrange themselves at distances that minimize overlap, reducing conflict while maximizing reach. Without sound, males cluster too tightly or spread too thin, unable to calibrate their positions relative to neighbors. When encounters happen, they are sudden and physical. Males stumble into one another at close range, triggering aggressive displays and wrestling bouts that would have been avoided entirely under acoustic order. These conflicts cost energy and time, and more importantly, they erode the stability females depend on when selecting mates. A calling site that shifts unpredictably is not a reliable place to deposit eggs. Breeding falters quietly. Females still produce eggs, but fewer are placed in optimal microhabitats. Poison dart frogs are meticulous parents, often transporting tadpoles individually to water-filled leaf axils or small pools that balance food availability against predator risk. That precision depends on timing and spatial memory reinforced by sound cues. In silence, routes overlap. Males interfere with one another's transport paths. Some tadpoles are deposited in suboptimal sites, too crowded, too nutrient poor, or too exposed. Survival drops, not catastrophically, but consistently. Predators respond in ways that are easy to miss. Poison dart frogs are famous for their toxicity and warning colors, but sound plays an indirect role in keeping them alive. Calling sites are predictable, and predictability allows frogs to choose locations that minimize accidental encounters with predators. Silence disrupts that predictability. Frogs move more during active hours, shifting positions as they search for mates or suitable egg sites. Movement increases visibility. A frog that would normally remain stationary becomes out of place, crossing leaf litter at the wrong time, exposing itself to snakes, birds, and invertebrate predators that hunt by chance as much as by intent. The toxins still work, but fewer predators need to sample them when the frogs are simply stumbled upon more often. This is where the damage becomes ecological rather than individual. Fewer successful matings mean fewer tadpoles, and fewer tadpoles reshape the smallest food webs in the forest. Tadpoles are not passive larvae. They graze on algae, bacteria, and detritus, regulating microbial communities in tiny aquatic systems that dot the forest floor. Remove them, and those systems tilt. Algae bloom more freely. Certain insect larvae proliferate. Water chemistry shifts, affecting which organisms can survive in pools that were once stable nurseries. These changes ripple outward, influencing insect emergence patterns that feed back into the broader ecosystem. The absence of sound also affects thermoregulation in subtle ways. Calling behavior is often synchronized with temperature and humidity cycles. Without acoustic cues to anchor activity, frogs mistime their exposure. They emerge at less optimal moments, risking dehydration or overheating. Dart frogs have permeable skin that trades flexibility for vulnerability, relying on precise behavioral timing to stay within safe physiological limits. Silence does not kill them outright. It nudges them into inefficiency. Over weeks, that inefficiency compounds. What makes this breakdown particularly insidious is that it leaves no dramatic signature. There are no mass die-offs, no sudden quiet that announces catastrophe. Populations dip slowly as recruitment fails to keep pace with natural mortality. Older frogs persist, masking the decline. From a distance, the system looks intact. Only long-term observation reveals the truth. Fewer juveniles reaching adulthood, fewer calls returning season after season, fewer bodies occupying niches that once seemed permanent. There is an evolutionary lesson buried here. Poison dart frogs evolved their toxins and colors to deter predators. But those defenses were layered atop a social system built on sound. Remove the sound, and the chemical defenses are forced to compensate for problems they were never meant to solve. Toxins deter attack. They do not organize populations. They do not space territories or synchronize reproduction. Silence strips away the invisible infrastructure that allows these frogs to function as a coherent population rather than a scattering of individuals. As recruitment falters, insects feel the change first. Fewer tadpoles mean fewer controls on aquatic larvae, which in turn alters the timing and density of adult insects emerging into the forest. Some species boom briefly, others decline, depending on which pools they depended on. These shifts feed back into predation dynamics, affecting spiders, birds, and even plants reliant on specific insect behaviors. The poison dart frog, tiny and easily overlooked, proves once again that scale is irrelevant in ecology. Influence is measured in connections, not mass. The twist is not that silence kills poison dart frogs, it is that it makes them quietly irrelevant. Their populations shrink not through dramatic loss, but through failure to replace themselves. The forest does not mourn them. It adjusts, reallocates, and moves on. By the time the absence is obvious, the processes that caused it are already entrenched. In this way, poison dart frogs become a case study in how ecosystems unravel without breaking. Sound does not just carry warnings or invitations, it carries structure. Remove it, and even the most chemically defended animals find themselves misaligned with the world they evolved to navigate. The damage unfolds in slow motion, written not in bodies on the ground, but in empty spaces where the next generation should have been. The eagle circles high above the Australian landscape, wings locked, primary feathers splayed to drink lift from a column of rising heat. From this height, the ground should feel alive, textured with information. Ripples in grass, sudden flickers of movement, the faint commotion of smaller animals reacting to one another. Instead, it feels blank. Not empty, but muted, as if the land has been wrapped in insulation. The sky hunter keeps circling, eyes sharp, posture patient, yet something fundamental is missing. The ground is not speaking back. Wedge-tailed eagles are celebrated as visual predators, and rightly so. Their eyes resolve detail at distances that reduce other hunters to guesswork. They can pick out a rabbit's ear twitch from hundreds of meters away, track the subtle shadow of a lizard slipping between stones, or lock onto the panicked sprint of a macropod fleeing another threat. But vision has limits, especially in Australia's grasslands and open woodlands, where cover is thin but deceptive. Sound fills those gaps. It confirms what eyes suspect. It exposes what hides. The rustle of grass out of rhythm with wind, the alarm calls of birds that have spotted danger, the sudden silence that follows a failed ambush. These are cues that refine the eagle's decisions before it commits energy to a stoop. In a functioning system, the eagle's hunt is opportunistic in the deepest sense of the word. It does not rely solely on chasing healthy prey. It listens for distress, for chaos, for moments when another animal has already lost the initiative. Kangaroos fighting, wallabies colliding with fences, birds mobbing a snake. These events generate sound that travels farther than motion alone. The eagle uses them like beacons, adjusting its patrol routes to intersect moments of vulnerability. Silence erases those beacons. From above, movement still exists, but it is incomplete, stripped of context. The immediate effect is subtle, but measurable. Prey freezes longer. In a quiet landscape, animals rely more heavily on immobility as defense, and it works. A rabbit pressed flat against earth becomes visually ambiguous without the confirming whisper of movement. A wounded animal that might have vocalized or thrashed now lies still, conserving energy and avoiding attention. For the eagle, this means fewer clean opportunities. The cost of investigation rises. Each descent risks wasted effort, and wasted effort burns calories that cannot be easily replaced. Carcass detection suffers even more. Scavenging is a critical, often underappreciated component of the wedge-tailed eagle's ecological role. These birds are not just killers, they are recyclers, removing dead animals before decay reshapes the landscape. Under normal conditions, carcasses announce themselves indirectly. Ravens gather and argue loudly. Smaller raptors circle and scream. Insects buzz in dense clouds. Sound draws the eagle's eye toward what might otherwise blend into the monotony of brown grass and shadow. In silence, carcasses persist unnoticed for longer stretches of time. The eagle flies past, unaware that an entire nutrient event is unfolding below. This delay matters. Death in ecosystems is not merely an endpoint, it is a process that needs to be managed. When large scavengers arrive quickly, they strip carcasses efficiently, reducing the window during which pathogens proliferate and opportunistic species swarm. When they do not, other actors take over. Ants form living rivers that carpet flesh and bone. Blowflies lay eggs in overwhelming numbers. Beetles burrow and breed. What was once a rapid transfer of energy up the food chain becomes a prolonged ground-level occupation. The domino effects ripple outward. Persistent carcasses become congregation points for insects and smaller scavengers, which in turn attract predators that would not normally cluster so tightly. Lizards, rodents, and birds converge, increasing contact rates and competition. The risk here is not dramatic outbreak, but accumulation. Parasites circulate more easily, stress behaviors rise, and minor injuries become more common as animals jostle in tight spaces. The eagle's absence from this phase of the cycle leaves a vacuum that is filled, but filled poorly. Thermoregulation intersects with this disruption in unexpected ways. Wedge-tailed eagles time their activity around thermal availability, using rising warm air to soar efficiently. Missed scavenging opportunities force longer patrols, pushing birds to fly during less optimal conditions. More flapping, less gliding. Higher energy expenditure with lower return. Over time, this can influence breeding success, territory size, and juvenile survival. A pair that cannot feed efficiently produces fewer offspring, and those offspring disperse into a landscape already struggling with slower recycling. The silence does not make prey safer in any meaningful sense. Animals still die from injury, disease, starvation, and predation by other hunters. What changes is how death moves through the system. Without the eagle's timely intervention, death lingers, flesh decays in place. Nutrients leach slowly into soil instead of being redistributed across the landscape through flight and excretion. The grass around carcasses grows unevenly, enriched in patches rather than broadly. Insects dominate the early stages of recycling, locking energy into lower trophic levels longer than usual. This shift reshapes behavior. Herbivores avoid areas heavy with insect activity, altering grazing patterns. Birds adjust nesting sites to escape ant infestations. Even predators modify routes, steering clear of zones that have become biologically sticky. None of this is catastrophic, but all of it is friction. Energy moves less cleanly. The system becomes noisier biologically even as it remains acoustically quiet. There is an irony here that cuts against intuition. Silence feels respectful, almost merciful, as if it grants animals peace. For a top aerial scavenger and predator, silence is inefficiency. It stretches suffering rather than ending it. A wounded animal that might have been quickly located and killed instead survives longer in pain, only to succumb later in isolation. A carcass that might have been stripped in hours instead becomes a slow-burn resource, intensifying competition among smaller organisms and increasing ecological congestion. Over weeks and months, these inefficiencies accumulate. The eagle adapts behaviorally, of course. It relies more heavily on visual patrols, focuses on open areas where movement is harder to conceal, and narrows its effective hunting window. But adaptation has limits. Vision alone cannot fully replace the distributed sensory network that sound provides. The eagle was never meant to hunt in isolation from the noise of life around it. Its success depends on a landscape that advertises its own disruptions. The broader lesson is not about sound as a hunting aid, but about cleanliness in ecological processes. Efficient predation and scavenging are forms of hygiene. They reduce lingering decay, minimize congregation, and keep energy moving smoothly through trophic levels. When silence disrupts that efficiency, the system does not collapse. It clogs, recycling slows. Interactions pile up in the wrong places. Risk concentrates rather than dissipates. From the sky, the eagle continues to circle, patient and powerful, unaware of the full scope of what has changed. It feels the difference only as effort without reward, as longer flights and emptier talons. Below, the land absorbs the consequences. Silence has not removed death from the landscape. It has made it messier, slower, and harder to integrate. In that way, the absence of sound does not spare the ecosystem. It burdens it, turning a finely tuned cycle into a prolonged, grinding process where nothing quite moves on when it should. The dingo moves through the Australian night with a posture shaped by expectation. Its head rides low, ears constantly adjusting, body angled not just to the ground ahead, but to the invisible positions of others moving with it. A hunt is never a solo act for long. Even when individuals spread out, they remain connected by sound, soft whines, breath patterns, footfalls, the faint cadence of movement that tells each animal where the others are without ever needing to look. Tonight, that connective tissue is gone. The land is quiet in a way that feels wrong, not peaceful but stripped, as if an entire dimension has been removed. Dingoes are often framed as visual coursers or endurance hunters, but that framing misses the core of their efficiency. They hunt with coordination first, speed second. Subtle vocal cues maintain spacing, prevent overlap, and synchronize commitment. A pack does not charge blindly. It compresses and stretches like an elastic system, members adjusting positions based on what they hear as much as what they see. The rustle of prey, the breathing of a flanking partner, the sudden acceleration of a runner. Sound turns individual movement into collective intent. Without it, the pack fragments into guessing animals sharing space, but not information. The immediate breakdown is timing. In a normal hunt, one dingo commits only when another has cut off escape or forced prey into predictable motion. Silence dissolves that certainty. Individuals rush too early or hesitate too long. Missed strikes multiply, not because prey is faster, but because coordination slips by fractions of a second that matter immensely when bodies collide at speed. The risk of injury rises. A kangaroo's kick lands where a partner should have been. A wallaby swerves unexpectedly, colliding with a dingo that misread its trajectory. These are not dramatic failures, they are awkward ones, and awkwardness is dangerous when muscle and bone meet at full force. Prey behavior changes in ways that further destabilize the interaction. Kangaroos and wallabies normally detect approaching predators early through sound, footfalls, breathing, the faint disturbance of grass. That early warning triggers flight before contact, initiating the classic chase that dingoes are built to exploit. Silence removes that trigger. Prey stands longer, uncertain. It does not bolt into predictable escape routes. It watches, tense, but still. For the dingo, this is unexpectedly difficult. Ambush works best when prey commits to panic, when fear simplifies decision-making. A prey animal that does not hear danger does not panic run. It pivots late, dodges sharply, and uses short bursts of power that scatter attackers rather than funnel them. The hunt becomes chaotic. Dingoes overshoot. They collide with one another. The elastic system that once tightened cleanly around prey now snaps unpredictably. Energy expenditure skyrockets while success rates drop. The pack still eats, but less efficiently, and inefficiency drives behavioral change faster than hunger alone ever could. Dingoes are flexible hunters, and when one strategy degrades, they pivot. That pivot reshapes the landscape. With fewer successful coordinated kills, dingoes increase scavenging. They follow roads where vehicle strikes provide carcasses. They patrol fence lines, creek crossings, and human-adjacent zones where livestock, refuse, or weakened animals are more predictable than wild prey. These shifts are not moral failures or bold expansions. They are compensations for lost sensory infrastructure. Sound once allowed dingoes to extract energy cleanly from wild systems. Without it, the easiest calories lie closer to humans. Conflict zones move accordingly. Areas that once saw little dingo activity become hotspots, not because dingoes are suddenly bolder, but because they are forced into narrower decision spaces. Scavenging brings them into contact with foxes, feral cats, and domestic dogs, intensifying competition and disease exchange. Roads become ecological magnets, concentrating risk for animals that would normally be spread thin across vast ranges. The absence of sound has not removed predation pressure. It has displaced it into places where the consequences are sharper and more visible. Physiologically, the cost is measurable. Dingoes regulate body temperature through pacing and rest cycles that assume successful hunts punctuated by recovery. Prolonged chases without payoff disrupt that rhythm. Overheating risk rises, especially in arid zones where nighttime cooling is critical. Injuries linger longer when food intake is inconsistent. Pups feel the effects first. Reduced provisioning slows growth, and slower growth narrows the window during which juveniles can safely learn complex hunting behaviors. Recruitment suffers quietly, masked by the continued presence of adults. The broader ecological role of dingoes complicates the picture further. As apex predators, they suppress mesopredators like foxes and feral cats, indirectly protecting smaller mammals and ground-nesting birds. When dingo hunting efficiency drops, that suppression weakens unevenly. Dingoes still exert pressure, but less predictably, and mesopredators exploit gaps with ruthless speed. The result is not a simple cascade but a patchwork of altered interactions, with some areas experiencing increased predation pressure on small fauna, even as others see temporary relief. The twist in all of this is that silence removes the predictable chase that both predator and prey evolved around. In a noisy landscape, fear has structure. Prey flees early, commits to flight paths, and either escapes cleanly or is caught quickly. Predators commit decisively, minimizing prolonged struggle and injury. Silence dissolves that structure. Encounters stretch out. Risk spreads across more individuals. Injuries accumulate on both sides. The hunt becomes less about skill and more about chance. From a distance, the land looks calmer, fewer stampedes, less audible chaos. But that calm is deceptive. It hides a rise in uncertainty that stresses every interaction. Dingoes are forced into improvisation, prey into vigilance without direction. Energy drains away in small, relentless increments as animals move more, hesitate more, and recover less effectively. Over time, this reshapes territory use. Dingoes tighten ranges around reliable resources, abandoning marginal areas that once supported them through coordinated hunting. This creates ecological vacuums where herbivores browse more heavily, altering vegetation structure and fire dynamics. Grass grows taller in some patches, shorter in others. The mosaic shifts, driven not by climate or rainfall, but by a missing sensory layer that once kept movement and pressure evenly distributed. Silence does not make the Australian landscape safer, it makes it less legible. For dingoes, that illegibility turns mastery into gamble. For prey, it replaces fear with confusion. And for the ecosystem, it trades clean, decisive exchanges for prolonged, risky entanglements that bleed energy at every level. The dingo adapts because adaptation is what it does. But adaptation has a cost, and that cost is paid in injuries, conflicts, and slow structural change. By taking away sound, the system loses its rhythm. The chase no longer follows rules either side can trust. What remains is chaos dressed as quiet, a landscape where nothing moves quite when it should, and everyone pays for the delay. The crossing looks ordinary, almost inviting. A wide bend in the river where the current slows, the bank slopes gently, and the water surface lies flat enough to reflect the pale sky. Tracks converge here. Hoofprints, paw marks, the scuffed lines of repeated use. In a loud world, this place would feel dangerous. Splashes would echo, birds would startle, the water would advertise itself as alive. Tonight, it feels blank. An animal steps forward with confidence it did not earn, hooves entering the shallows where caution should rule. This is a crossing that should never happen. Saltwater crocodiles are not ambush predators in the way cats or snakes are. They do not rely on sudden concealment followed by explosive speed alone. They are detectors, living tripwires tuned to vibration, pressure waves, and low-frequency sound at the waterline. The skin along their jaws is studded with integumentary sensory organs that register minute disturbances. The oscillation of water displaced by a footfall, the ripple of a tail swish, the faint tremor of something breathing too close to the edge. Vision matters, but it is confirmation, not the primary trigger. The river speaks first. The crocodile listens. Prey, meanwhile, has evolved to treat water as an alarm system. A drink is never silent. Hooves disturb sediment, muzzles break the surface. The smallest misstep sends ripples outward, and those ripples are information. They tell prey that the water is reacting, that something beneath may be reacting as well. Animals approach slowly, pause often, retreat at the first ambiguous signal. That half second of uncertainty, the moment between disturbance and confirmation, is where most lives are saved. Remove sound and vibration, and that half second disappears. In silence, animals approach water with an ease that would normally be punished immediately. They step closer before stopping. They lean farther forward. They lower their heads without scanning the surface for telltale rings or sudden movements. Confidence replaces vigilance, not because danger is gone, but because the cues that once translated danger into behavior have been erased. The crocodile benefits from this not by becoming faster or stronger, but by being allowed closer. The strike distance shortens. Crocodiles that might have launched from 2 meters away now wait until 1, some wait until less. The mechanics of the attack change subtly. Shorter strikes mean less water displacement, less warning even for nearby animals, and a higher chance that the jaws close on something vital. Near misses increase too, swipes that graze, explosions of water that send prey scrambling, but even those misses reshape behavior. Survivors flee not from sound, but from shock, and shock does not teach as effectively as warning does. They do not learn where the edge of safety lies. They only learn that death is sudden. This produces a paradoxical landscape. Fatal encounters become more abrupt, but the overall sense of danger decreases. Animals remember nothing before the strike, because there was nothing to remember. No splash, no ripple, no warning call. The river becomes falsely neutral, a surface rather than a boundary. More animals approach, more crossings are attempted, more drinking occurs at the same few edges where access feels easiest. These sites accumulate pressure quickly. The domino effects start at the bank. Repeated use compacts soil. Vegetation is trampled down to roots. Without plant anchors, erosion accelerates, undercutting the bank and sending sediment into the water. That sediment clouds visibility for species that rely on sight, alters oxygen levels for aquatic organisms, and changes the thermal properties of shallow zones. Crocodiles adjust effortlessly, others do not. As drink sites degrade, animals funnel into the remaining safe edges, places where the slope is shallow or the substrate feels stable underfoot. Clustering intensifies. Herbivores jostle. Predators wait at the margins. Disease risk rises not through any single pathogen, but through proximity and stress. Animals spend more time waiting their turn, less time feeding or resting. The cost of hydration increases across the ecosystem. The crocodile's role in this shift is unsettlingly passive. It does not chase animals into these clusters. It does not need to. Silence does the work. By removing early warning cues, the system encourages repeated risk-taking until risk becomes normalized. The crocodile simply occupies the consequence. Thermoregulation weaves through this story as well. Crocodiles balance body temperature by selecting basking sites and controlling time spent submerged. Increased hunting success at shorter distances reduces the need for prolonged patrols, allowing more energy to be allocated to growth and reproduction. Larger individuals dominate prime river stretches, displacing smaller crocs into marginal habitats where they take more risks or turn to alternative prey. This reshuffling alters pressure along entire river systems, affecting fish populations, bird nesting sites, and even vegetation patterns shaped by nutrient redistribution from carcasses. For prey species, The loss of warning does not just change behavior at water. It bleeds into movement patterns across the floodplain. Animals avoid long crossings and concentrate activity near permanent water, even if it is dangerous, because uncertainty elsewhere feels worse than known risk here. This spatial compression amplifies grazing pressure, stripping ground cover and exposing soil to sun and wind. Fire dynamics shift. What began as a sensory disruption at the waterline becomes a landscape-scale transformation. The most disturbing aspect of this quiet river is how clean the kills become. There is less thrashing, less prolonged struggle. Death arrives in a single motion more often than not. From a purely mechanical perspective, this seems efficient. From an ecological one, it is deceptive. Clean kills remove learning opportunities. Survivors do not carry forward the memory of close calls marked by sound and movement. They carry only absence. The system loses its feedback loop. Nature runs on half-seconds, on the tiny delays between stimulus and response that allow animals to choose differently next time. Silence deletes those margins. It compresses decision-making to the point where there is no decision at all. Step forward, and you are alive. Step again, and you are gone. There is no adjustment between. Over time, this reshapes fear itself. Fear becomes location-based rather than cue-based. Animals avoid entire stretches of river rather than responding dynamically to conditions. That rigidity is costly. It reduces flexibility in droughts, increases competition in safe zones, and leaves fewer options when conditions change suddenly. The crocodile thrives in this rigidity. It has always been an edge predator, and silence sharpens edges. What makes this especially unsettling is that the river looks calm throughout. No splashes advertise danger. No sudden eruptions of panic ripple outward to reset behavior. The surface remains smooth, reflective, almost benign. To an observer, it appears safer than ever. That appearance is lethal. The final truth is not that silence empowers crocodiles. They were already perfectly equipped to kill. The truth is that silence disarms everyone else by erasing the last usable fraction of time. The warning that turns approach into retreat, curiosity into caution. When that fraction disappears, nature does not become quieter. It becomes unforgiving. The quiet river crossing that should never happen happens again the next night, and the next. Tracks deepen, banks crumble. The crocodile waits, unmoved by any of it. Silence has done its work long before the jaws close.